Hello, everyone. Welcome to this AWMA's 114th annual conference virtual presentation on automated AERMOD model setup for complicated scenario analysis and case studies. My name is Chi Zhang, and I'm with GHD. First of all, please allow me a few moments to introduce a little bit of GHD and myself to you. GHD is an international engineering company doing a lot of business in environmental compliance, including air quality work. About myself, I have over 10 years of experience as an engineer or consultant in air quality work, doing permitting, dispersion modeling, and other works. And if I have luck to have you as one of my previous presentations audience, you might also know that I have also some experience in photochemical grid modeling for interprecursor trading in non-attainment ozone areas. So let's get started. So agenda or key takeaways for today. So where is the change we're talking about? And why do we talking about automate some of the setup for AERMOD? And three, what tools do we have? And I'm going to share some case studies with you. And in those case studies, we will talk about what programs did we develop and how does it compare to traditional alternatives. And at last, we will outlook what's the next steps of those works. So first, where is the change? So on the slide, you will see a very traditional workflow of AERMOD. We first get metadata processed with AERMET and get some model-ready surface profile data. We have terrain data processed with AERMAP to get elevations. We input buildings and run them with BP and BPIP to get our downwash parameters. And all of those are base data that supports our AERMOD run. Of course, we want to input our source locations, giving AERMOD our source parameters, emission rates. So questions are, so traditionally we just need to put in those source locations, source parameters, and emission rates that's known. What if those parameters are unknown, like unknown locations about, flexible stack heights, or source operating, scenarios are different? We want to evaluate multiple operating scenarios, or if there is any kind of separate or combined stack options that this client has not decided on. So all of those unknown, variables will create a lot of, complexities to the model, and we will be looking at how to efficiently, to set those models up instead of manually enter all the data. So on the rear end, also we will have the AERMOD run and get our output file, or sometimes summary files, and we have contour plot files and exceedance maxi files. Of course, there are also other types of files we will be getting from AERMOD. So from the front end, if we have a lot of different, uncertainties that will result in various model inputs, then we will have a lot of outputs coming out from there. So is there any ways that we can process large amounts of the result data efficiently? Here, basically, the left box, this box of questions and these questions are where is the change question we would like to answer. Why automate? Okay, so this is basically answering the questions in the previous slides, that boxes. So the benefit of doing automate of AERMOD setup is, so combination of multiple variables in the model input really creates many scenarios. So in order to handle those many scenarios, we want to automatically maybe write source groups to address those different scenarios. Or in some cases, source group won't work, then we would like to need to write the input files, but a lot of input files. For example, when ARM2 is turned on, in the NO2 modeling, you won't be able to do source groups. That's where, you have to do multiple input files, and, we'll see how the automate will help. And also by automating, we can create model runs for multiple pollutants with the same source setup, just like in one click. You don't have to set up all the different, input files again and just change the emission rates. Instead, you can have a program that can create all the, files for you. And also the benefits including we can also gather the results from multiple AERMOD output files, from multiple maxi files, from multiple plot files at the same time. Another key benefit is to minimize human mistakes. Apparently as modelers, we are all very good at, paying attention to details. However, human beings will make some mistakes, and that can cause some issues down the road. So by using a computer program to write multiple input files and post-processing results, getting results from the run, that really minimizes the possibility of making the mistakes, as long as we make sure the programs was written correctly. So hours and hours of human labor really can now be one click away. That's really a benefit. And really thank you to one of my presentation reviewer from the technical program, to add at this point. Really, nowadays, some clients are having really demanding construction schedules, and by using automated AERMOD setup, we will be able to identify design options that will work with permitting much earlier in the game, and that will save time in the air permitting process, so that we will be able to meet the demanding construction schedules. That's considering the site will be built from scratch, and none of the design is anyway finalized. So what tools do we have? Well, programming languages such as Python, I'm putting Python here because I use Python a lot. However, like C or Java or any other great programming language can all serve the same purpose. They have really great capabilities to read, write, and evaluate the AERMOD input and output files, as well as they can navigate a file directory to realize multiple file operation at the same time. This presentation, I use Python as an example, and I will provide some generic ideas of writing some customized programs to assist with your implementation of AERMOD modeling analysis. So here, let's discuss about 2 case studies, and on each of the case studies, we will discuss what automation did we create, how do they compare to traditional approach. So the first case study will be focused on the front end, putting together all the inputs, whether it's source groups or multiple input files for the model to run. And the second case study, we will be looking at a program on post-processing the model outputs, getting the results, frequency of exceedance analysis, all those kind of different, utilizations. Okay, so case study 1, the project background. So one disclaimer is both case studies was coming from some real life example. However, I abstracted the concept to make up some of the concepts due to the project confidentiality, but the key point is very similar. These examples are abstracted hypothetical examples. So for this case study 1, okay, so we have a facility. They are under the design phase, and they want to get their air permit quick, so they don't have their design finalized. So all we know, okay, so we will have 2 RTO stacks, but in 4 different possible locations here, in here, the 4 different dots. And we'll have, here we have 10 different furnaces to melting some metals, it could be 10 separate stacks, or they could have an option to route them to 2 combined stacks with apparently higher flow rate, and therefore maybe better dispersion parameters. And also they will have emergency engines as a set of emergency engines at 4 different possible locations, 1, 2, 3, 4. And of course, there will be various stack heights that's possible, and the client is also thinking about. But maybe we will not, get into, the stack heights variations to make this example simple. Okay, so all these are open-ended design. Design team will tell us, hey, let's evaluate all the possible evaluation, do all the evaluation and all the possible, possibilities, and let me know which possibilities, which combinations of those stacks, locations, and configuration will work for permitting purposes. So design team is the design team said we will be relying on the air quality, the modeling results to finally design where the stacks are and the heights and all those other parameters. Okay, so what's the traditional approach? Traditionally, we usually pick up some locations because we think maybe it's not that feasible to do the math and find a combination and kind of like to input, to set up all the different input files for AERMOD, set up all the source groups, that can contain all the different possibilities. So we will try to pick the locations that are likely to result in the worst case. So here is what we do. See, we put the 2 RTOs down here, and if we call this is upward is north, so we probably we put it close to the south end of the boundary, and we put this engine here because to kind of try to not selecting here is because we want to cluster the engines, the RTOs, and these furnace stacks all together so that they will have a strong synergy to impact offsite concentrations. And of course we select the separated 10 separate stacks for the furnace. So this is kind of like conceptually it might result in a worst case model. So considering all the sources are clustered together, they are close to the boundary, but are we having 100% confidence this really is the worst case? So some questions to ask. What if, in case the wind direction is from south, from this? So in that cases, we may want to consider, the worst case, impacts are over on the north end of the boundary instead of in the south. That way, the worst case configuration could be engines moving up, and I use these 2 locations for RTO instead of this 2. What to do with that? And will worst case setup for short-term impact be the same for long-term impact? That being said, my 1 hour NO2 model, will that have the worst case location at the same as its annual NO2 model? What if they are different? What am I not, by using just one scenario, am I missing anything? And also, really, does the emergency engine contribute these guys enough to warrant the selection of RTO location towards these cells? What if those emergency engine, for example, if they are doing like 50 hours per year, we could use intermittent guidance to categorize NO2 emissions. So in those cases, maybe they were not really worth to be considered together. So we would need to be really thinking about RTOs or furnaces, so maybe it's by thinking about putting them in the south because of this is so close to the boundary. Does it worth to do it? Maybe it's not going to make a whole lot of difference in the final results. So maybe our worst case, another scenario. So there might be other challenging questions from the reviewing agency. Agency will come up and say, hey, can you give us, enough justification on how you come up with your worst case? It's sometimes really hard to argue. So what we do. So let's think about these things again. Okay, so RTOs, we have 4 different locations, but we want to pick 2. So that's a combination of 4 choose 2. That's a total of 6 options. And then we have 4 options for engine locations and 2 options for furnace setup. And like we discussed earlier, for this example, we are not going to vary the stack height just for simple purposes. So the total scenarios to model, we do the simple math: 6 options times 4 options times 2, 48 different scenarios. Well, in real life, the number really can be hundreds, thousands, or even more. But as today, nowadays, the computational power really advanced, and it is now possible to run all the different scenarios with a reasonable time frame. And we may have the local computer with more than 100 logical processors, or we nowadays can send those AERMOD run to cloud services to make them faster. So our goal is to evaluate all the different combinations, and then after we got the results, we pick where the worst case. That way, it's the most defendable answer to the state agency. Here, see, we have run all the possible scenarios, and here is the worst case results. We don't have to worry about if the we picked, the human picked, that scenario is the worst case or not. So here is some coding tips that I use in the Python to write the different, write the different source groups or input files just with one Python program. The key is to use a loop. It doesn't necessarily be in Python. It could be other programming language. In Python, you will use a for loop, and you have to use loop in the loop for multiple levels of a loop to loop through. First loop through RTO, and then loop through engine, and then different furnaces. So for every selection of RTOs, like for example, in A or B, any and B location, I have 4 different, and then first, looping through the RTOs. When the loop goes to the first option of RTO, it loops through the engines, engine 1, 2, 3, and 4. And actually, when the model is the program looping through the first option of RTO, the first option of engine, it loops through the furnace. So it's a multiple level of loop. So the combination really can be customized to fit different project needs. So by writing that program, and all you have to do is just give it to other modelers, just let them just to double click or one click on your program, it'll run and create all the different 48 or 300, 3000 input files, or write 48 lines of source groups, 300 lines of 3000 lines of source groups to be included in the AERMOD file. So that's the front end example I would like to share with you. So the next case study, we want to more focus on the rear end. The project background is, this is a surface coating facility. The surface coating facility, they use a lot of different painting products, and they will send us all the SDS information or air quality data sheets with all those different chemicals, speciated chemical in there. And in some states, here, the example, the project I was doing was in Texas. It requires to evaluate all the speciated chemicals for ambient air impacts and comparing to the state guideline standard. In Texas, it's called the effect screening level, ESL, but it could be any kind of standard or guidance level that in any other states or any other country. So, but here for the short-term analysis in Texas, the requirements at that location of maximum ground level concentration is in this table. So, it allows you to exceed the 1 times of the standard, but you couldn't, for example, in this type of land, industrial area, overland industrial area, you can, have concentration, or your model impact up to 10 times the standard. But also you need to look at your frequency. You have up to 24 hours per year of allowance that is over the 2 times of the standard. And you can have up to 10 hours per year of modeled, that the year means the modeled metadata year to exceed 4 times the standard. Of course, they have other land use, like over water, it has a much looser, criteria, like 25 times the standard. And, but on non-industrial area, the guidance will be more stricter. So what we need to do, we need to run the model, we set up the maxi files, and we need to find out how many hours are exceeding, say, 1 times the standard, 2 times the standard, 4 times the standard, 10 times, 25, and 20, all the times that you can name. So traditional approach is we'll set up a site-wide model. Let's just say 1 stack, the paint booth stack, regardless of whether it goes through an RTO or not. Just like that stack has a stack parameters, it emitting all 250 plus chemicals. We'll use the real stack height, diameter, velocity, and temperature, but the emission rate, we keep it like 1 pound per hour for just a generic pollutant. And then we set up a source group for every source in the model. Okay, so I just said I use a simple example, but in other cases, if you have 2 stacks or 3 stacks or more, you definitely can set up that source group for every source in the model. And there is no need. It doesn't make any sense to have the all group because it's just like 1 pound per hour. And run the model and get the unit emissions impact, so-called UIM, or like unit emission impact multiplier, and do the math. You put together a table, and for every pollutant, its emission rate, and its UIM, and you times these together and add all the different sources together. This is a really conservative approach. And the good thing is, if the overall screening impact calculated from this method, the table I just described, can pass the criteria set by the state, then we're good. And this could really, filter a lot of chemicals that we don't have to really worry about. So, for example, most of the chemicals use this approach screens out. So we have about like 30 chemicals left with the screening impact over that standard. So the next steps, in the traditionally, so for all these, we throw them into the model, AERMOD, doing refined model that now it'll take account of take advantage of AERMOD's, ability to pair the time and spatial, pairing, so that, not necessarily, the overall impact is all those worst case impact, add up all together. So this can be done in some third-party AERMOD GUIs, graphic user interface softwares. And I have been lucky enough to have done most of those, software that I really like those. Also, but also on the other hand, if you want to have more freedom on your own kind of like problem design and things like that, you could possibly to write a Python code to generate all the input files based on reading of a spreadsheet as well. But that we can talk about in another topic and how to do that. And after the models are set up, okay, so all the 30 model runs are set up and they send it to run. Of course, you need to set up maxi files the maxi files, you give the threshold at 1 times that standard. Okay, you get the maxi file after the run. Then what you can do is traditionally, I did this. I copy the maxi file into the spreadsheet, into Excel, and then I count. Okay, so I sort it and I count it, all the hours of exceedance is at this location. Remember TCEQ, the Texas, they want to look at the impact on this, worst case location, but you could do any location because the maxi file will tell you other location information as well if they exceed that level. But this is really tedious work. Some software can process the maxi files to really count the hours exceeding like different multipliers of the standard, or a user specified multiplier of your standard. But it might require you to process one maxi file at a time. And there are also other software that allows a multi-chemical option. But our experience was we sometimes need to set up a different place, maxi file setups. Sometimes have to set up a source group to duplicate to basically create different maxi files and at different thresholds, like 2 times, 4 times. So the program that I personally developed was able to just run through all the maxi files that you created from a model run, and you have all the maxi files saved in a single directory. And remember, we talked about Python can, or whatever other programming languages, they can operate all the files in one single directory very efficiently. So the program that you can create on your own have some benefits. Okay, so it can run through all the maxi files. Well, regardless of file names, you don't have to tell which file to run. Just tell them, okay, this is a .max. That's a maxi file. Okay, so run through all the maxi files and do that job that I just described in the previous slide. Just do it and allow multiple chemicals to be processed simultaneously. Just one click, and all on a sequential batch basis, it process everything with one click, and you can review. You can create a table like here in here. Like you can, okay, so this is the file that I just processed. What is the ESL and what is the GLC max, the ground level maximum concentration? Is how much and where it occurred. And okay, so then I can sorting through all the data, how many times it exceeded, 1 time the standard, 2 times the standard, whatever standard you want. And in your input file, you want to write the names of the pollutant you want, and like here IND means industrial area, NI means non-industrial area, but these can be the names that you give to the AERMOD input file, and that you can understand those, and you can have a list of. Here I only showed 4, but most of the times I will have more than hundreds of maxi file that processed at the same time. And instead of we can and it's really quick, and like with the Pythons that kind of file reading and writing kind of that module, it's going really quick and create a internal, like a Python can create like a small back end database, and it can run through the data and give you the answer really quick. My experience, if you're only looking at the location at where the maximum concentration is, this means like on every maxi file you only look at one location, which is the worst case location. And with 30 to 50 maxi file, it takes very quick to run, like unless as long as you set up the threshold reasonably. If you set up threshold at 0, then apparently it'll give you all the receptors at all the 87, 60 hours for a whole year. Then that is going to run for a little while. So that is the case study that I would like to share with you, and I want to also give some coding tips on this as well. So the maxi file. So a very interesting thing is, okay, so the maxi file, when you tell it the threshold in the input file, you can actually find that threshold in the maxi file. So use this, we can use this line split function in Python to read the threshold from the maxi files, and actually you can write that in this table, so that you have a really good reference. So look at the fourth line at the last, towards the end, you have the ESL or the threshold you give it to him to the AERMOD input file. And interesting thing is, like here me just saw the fourth line of the maxi file, but I picked here when counting the line in Python, I said x equals to 3. That's because Python really starts from 0, so that it's kind of like 0, 1, 2, 3. So the fourth line is really in Python means the third line, but that's all those programming tricks that you will really get used to when you do more and more of this. And also another key point, to run through all the maxi files in one directory, or you can run through all the summary files that you created, or run through all the plot files you created in one directory. You don't want to run those maxi files or summary files one by one. So use some sort of file processing in one directory, those module. In Python, it's the OS, and here is a simple code that you can use to create that. This is basically the two case studies that I would like to share with you guys on this presentation. And okay, so what's next? We have explored all these front end, rear end. Apparently there are more and more functions, unique functions that we can try. And the way you write your own program, the benefit is it's all open and you can do all the things you want. So, and you will really enjoy it if you get used to it. I would like to explore and develop more useful tools to fit more unique purposes for AERMOD input setup and output processing. And after that, this is what I want to do looking forward is nowadays the artificial intelligence and machine learning really is a very hot topic. Maybe in the future in this conference, or other like a special modeling conference, I would like to also explore and maybe present my findings on if what AI or machine learning can help us for dispersion modeling. But that's future work, and if you have any good idea, let me know, and I will be very happy to discuss with you. Okay, so this is all for my presentation, and if you have any questions, please send me a note, and I will be looking at your questions and get back to you as soon as I can. And again, thank you so much for attending this virtual presentation. I look forward to hearing from you guys. Thank you, and have a great rest of your conference.